Component A of Unit 2 covers probability and statistics. So take a read through this question. As usual, read it through a couple of times, perhaps at least 3 times would be a good idea. So if you want to pause the video at this point and read through it yourself, that would be a good idea. Straight away, you should notice that this question has a slightly unusual structure in that it looks like a very short question as it's written on the page, just 3 sentences, but we're being offered a suspiciously large number of marks, 11 marks. That's enough to raise anyone's suspicions, and what that usually indicates is, well, potentially a couple of things. Number one, it's usually an indication that this is a relatively difficult question and possibly relates to some of the more advanced material on the syllabus. But secondly, we're not going to be given 11 marks without showing a lot of working out, without showing a lot of steps, a lot of structure. Because there's not much structure in the question, it's down to us to incorporate an appropriate level of structure in our answer. Let's take a closer look at the question. The key giveaway phrase is here. This question is all about hypothesis testing. Whenever you see this aspect of Unit 2, and it'll crop up in later probability and statistics units, you've got to straight away start thinking of structure. I'm going to show you a detailed step-by-step structure that I think you should adopt for hypothesis testing questions of this nature. Step number 1 would be to define a suitable random variable. At this point, of course, it's essential that you understand the meaning of this 2-word phrase. What is a random variable? If you're not too sure about that, this might be a good opportunity to go away and revise that whole area. Make sure you understand what the random variable is. Otherwise, you will only have a limited grasp of how hypothesis testing works. But I'll assume we're in a good place with random variable. We understand what that means. The first step in questions like this is always to define a suitable random variable. By define, I mean that you have to use a form of words explaining what your variable is. So in this case, we would choose this. Have a careful look. I'm using the letter X to represent the random variable. It's common practice with random variables to use an uppercase letter. This is definitely an uppercase letter X. It may be that you're a little bit aware of the difference in usage between uppercase and lowercase letters in probability and statistics. If that's something you find confusing, that's often an indication that you haven't quite grasped this concept of random variable. So keep working away at that. But I will be using a capital letter X to denote this random variable. So random variable relates to a random experiment. In this case, the experiment is defined there in the first half of the first sentence of the question. Vinita threw a coin 15 times. That's the random experiment. And the random variable associated with that experiment is some measurement of the outcome of the experiment. And the measurement that we're being told to look at is to count the number of heads obtained in those 15 tosses of the coin. There's a few issues here. A glance through the question shows you that there are 3 numerical pieces of data there, a 15, a 13 and a 1%. And students often get confused about the roles of these various numerical data values. It's the 15 that we need at the moment and not either of the other 2 numbers. The 15 is a fixed parameter of the problem. The experiment was definitely 15 tosses of this coin, and that will not change during the course of this question. We now need to define a parameter to test essentially what the hypothesis test is based on. I am happy to accept that when you've done this sort of question before, you may have got the step I'm about to write down and the step after it, maybe you might have put them in a different order. That's absolutely fine, but I'll show you how I would do this. I would define a variable to denote the proportion of heads achieved when tossing this particular coin, the one that was used in the experiment. You may be a little bit puzzled why I haven't used a lowercase letter p here, and why I haven't just referred to this as the probability of achieving a head with that particular coin. You could do that, that's absolutely fine. There is a reason why people don't use a lowercase letter p here. A lowercase letter p in hypothesis testing is often used to denote a different quantity, which we'll pick up on a bit later on. And strictly speaking, the variable here, what I'm referring to, the parameter to test, is the binomial proportion parameter. Okay, but it is often referred to as a probability. So hopefully, when I show you the next step, this might tie in a bit more clearly, just in case you're sensing something a little bit unfamiliar. So my next step would be to identify the distribution of my random variable x. It should be clear to you from your understanding of probability and slightly more complex probability situations that crop up in Unit 2 that x has a binomial distribution. And the parameters of the binomial distribution are n is 15, that's the number of tosses of the coin, and the probability of achieving a head each time we toss the coin is theta. As I mentioned before, you might have preferred me to use a lowercase p where I have used a letter theta. That would be absolutely fine, it's not a big problem. It may be that at this stage you would have preferred me to put a numerical value in place of theta inside that bracket on the last line there. That's not really the correct thing to do. At the moment, what's agreed upon, what, if you like, Vinita and Mark and we all agree on, is that x is a binomial random variable with parameters n equals 15, but the proportion parameter, which you might call p or theta, is unknown. We don't agree on it at the moment. So we need to write this down before the next step, which again, any familiarity with hypothesis testing will suggest that you've come across the next step before. I'm going to write down the two hypotheses, the null hypothesis and the alternative hypothesis next. So you should recognize that the null hypothesis in this case is this. Remember, we always write null hypothesis, capital H subscript 0. The null hypothesis in this case is theta is 0.5. That would correspond to the model the coin is fair and unbiased. In other words, that's not what Mark is claiming. The null hypothesis always corresponds to the sort of default situation, the no change situation, and perhaps the most obvious model statement. So in our case, the alternative hypothesis is indeed Mark's claim. Mark is claiming that the coin is biased in favour of heads. So he believes the probability of achieving a head each time we toss the coin is more than 0.5. So if I were to write that in the usual way, the alternative hypothesis, which we denote by capital H subscript 1, is theta is greater than 0.5. Because I've got a greater than symbol there, this is what's known as a one-sided or sometimes a one-tailed test. If Mark were claiming that the coin were biased in favour of tails, then the alternative hypothesis would be theta less than 0.5, but that would still be a one-sided test. If Mark were just claiming that the coin was biased, then the alternative hypothesis will be theta not equal to 0.5, and then we would have to use a two-sided test. So for our purposes, things are about as simple as they can be. It's going to be a one-sided test. Okay, you need to familiarize yourself with these 4 steps. I believe they should be written down in this order. Okay. Next, we want to move on and we want to make some calculations. Now, it's only possible to make some calculations, by which I mean calculations of probability, if we do, in fact, know the distribution of x. So at this point, absolutely crucially, we make an assumption. We assume that the null hypothesis is true. Note that we never assume the alternative hypothesis is true. The assumption at this point is always that the null hypothesis is true. So in that case, rather conveniently, we now have a specified distribution for x. We are assuming that x is binomially distributed with parameters 15 and 0.5. Let's move forward a little bit. I'll put that last line up at the top of the screen to make myself more space. I've left the question at the top. So we're now going to move forward working on the assumption that the null hypothesis is true. So that x has exactly this distribution. It's at this stage we need to pick up some more information from the question. We are told that the observed value of x, the observed value of the random variable in the experiment, the random experiment, is in fact 13. Okay, and we use that information in a really crucial way. A typical phrase you can use is something like this. If we conducted the experiment again, the probability that the evidence would be, quote, as bad or worse than this observation is this. So you might want to stop and think about this for a little while. So Vinita has done this experiment once. She has thrown a coin 15 times. And what happened was she got heads 13 times and presumably tails twice. If she were to undertake the same experiment again, we wouldn't expect her necessarily to come up with 13 heads this time. That's what makes it a random experiment, and that's what makes the value of x a random variable. As bad or worse means at least as far away from the null hypothesis observation. Now bear in mind that for a binomial distribution with parameters n equals 15 and p equals 0.5, tossing a coin 15 times, I would expect on average to have got 7.5 heads. The observed value, 13, is definitely bigger than that. So by worse than, as bad or worse than 13, I mean x, if I'm interested in the probability, if I conduct the experiment again, or if Vinita conducts the experiment again, what's the probability that she will get at least 13 heads, by which is meant 13, 14 or 15. So I've got a random variable x, I know full well its distribution there towards the top of the screen, and I'm asked to calculate a probability from that distribution. Okay, there's a few different ways of doing that. I'll show you what I think is perhaps the most efficient way of doing it. First, you should recognize that the probability that x is greater than or equal to 13 is 1 minus the probability that x is less than or equal to 12. It's always easier to calculate what are called cumulative probabilities. The probability that x is less than or equal to some value. So do you understand the last line that I put on the screen there? In case you want some clarity, here I've just depicted a little number line. This displays the possible values of x. If I toss a coin 15 times, I might get 0 heads or 1 head or 2 head or all the way up to 15 heads. We were asked to calculate the probability of getting either 13 or 14 or 15 heads. I am suggesting to you that that's 1 minus the probability of getting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 or 12 heads. And the reason for that is that the set of values x is 0 to 12 is the complement of the set of values x is 13 to 15. And the probability of those complementary events is, of course, 1. Okay, so hopefully that's clear. So here's how I would suggest is the efficient way to answer this question, to calculate that sort of probability there on the right, probability x less than or equal to 12. I think you should have a go using your calculator. So assuming you've got the recommended type of calculator, get it in front of you and do this sequence of key presses. Switch it on if it's not already on. Hit the menu button, which is to the left of the on button. Choose option 7, which says distribution. Okay, from there you'll see a menu of 4 options on the screen. You don't want any of those, so you move the down cursor onto a new menu. From that new menu, where there are 3 options, you choose number 1, which is binomial CD. That stands for cumulative distribution. And then it'll give you 2 options after that. You choose option 2. It'll then show on the screen the values that you need to input to calculate a binomial cumulative probability. We need to enter the value x equals 12. So your cursor will already be on the row corresponding to x. You type 12, then equals. The next row down is the value of n for the binomial distribution you're dealing with. So that's 15 in our case. So we type 15 equals. And then it says p, which is the binomial proportion parameter, which I previously labelled as theta. So we want 0.5, then press equals to enter that. And if you hit equals one more time, your calculator will give you that probability on the screen, which is 0.996307373. So a fairly high degree of precision. So remember, we want the complement of that. We want 1 minus that. And that will give this rather small value, 0.003 and so on. I'll show you one more way to evaluate this probability. It's always good to have a backup method, even if you're completely confident with using your calculator. There is another method that the examiner would like you to be familiar with and well practiced with, and that's the use of the binomial tables. So in the exam, you'll have a set of printed statistical tables. Like everything else, you need to make yourself familiar with it. So hopefully you've got a copy of the statistical tables either printed out or online. So have a good look through. The first few pages deal with the binomial distribution. In the WJC statistical tables, it's called Table 1. In fact, it's a set of several tables. And you need to page through to find the table where the left-hand column is labelled n equals 15. Because that's the binomial table corresponding to the value n equals 15. Remember, we're tossing a coin 15 times. And then the different columns in this table give different proportion parameters for the binomial distribution. That's the p, or the theta, if you like. And remember that in our case, here it's still on the screen there towards the top, we want the proportion parameter is 0.5. Okay, so we are only interested in that final column in this table here. And then going down either the left-hand side or the right-hand side of the whole table, those are your values of x. And these are cumulative probabilities. So the top probability is probability x is less than or equal to 0, then probability x is less than or equal to 1, then probability x is less than or equal to 2, and so on. So we want probability x is less than or equal to 12, and to 4 decimal places the table tells us that the probability is 0.9963. Have a look at the line above. Fortunately, that agrees with what the calculator told us. This value that we have calculated, the probability that x is greater than or equal to 13, in other words, the probability that when I conduct the experiment again, I will get evidence as bad or worse than the observation that Benita had, is called a p-value. That's why I resist the temptation to use the letter P earlier on. Now, you don't have to use this phrase p-value, but you do have to show an understanding of what this probability represents. It's the probability of obtaining evidence as bad or worse than the observation stated in the question. Now, what usually happens in hypothesis testing questions is this probability is pretty small. So 0.00 something. So just to make it a bit more readable, it's quite common at this stage to convert this into a percentage. So it's 0.369% to 3 significant figures. That's more than enough. And then this is the point at which we're going to use the one last bit of numerical data given in the question. We were asked to test the hypothesis at the 1% significance level. That means I need to compare this p-value with 1%. It should be very clear to you that our p-value is less than 1%. In this case, that means the calculated probability is very small or small compared with the threshold that we have been given. So the probability of the event we're calculating is a very unlikely event. So this leads us to reject the null hypothesis. What we're saying is it's very unlikely that we would get 13 or more heads if we throw this coin 15 times, assuming it's a fair coin. That probability is very unlikely. It's less than 1%. So we don't accept the null hypothesis, and the key word to use here is reject. We reject the null hypothesis. And you also need to put in another standard sentence here. You need to say something like this: we conclude that at the 1% significance level, the coin is biased. So we relate our finding to Mark's remark in the question. And that's it. Following through those steps very carefully, one by one, that should get us our 11 marks. Let's review some of the core skills that we needed to apply to the solution of this question. First and foremost, as I hinted early on there, I think random variables is at the heart of any advanced probability or hypothesis testing question like this. Please make sure you've got a reasonable grasp of the concept of random variables. Without that, you won't really have a good understanding of any of the more advanced aspects of probability. The next key component here was binomial distribution. You really need to understand what a random variable is before you can understand any probability distribution. Binomial distribution should be one of the first, perhaps one of the 2 or 3 first standard distributions that you came across in Unit 2. And you need to have a pretty solid understanding. Again, if you're not so confident of that, take a step back and do some of the more basic questions on binomial distribution to make sure you've got a good understanding of that and that you know how to calculate probabilities for a binomial distribution. Really key thing, I think, here for hypothesis testing questions, I drew attention at the start to the fact that the question is short and relatively unstructured. It's your job to put that structure in. in general, things like that, we call this sort of thing modelling. We're trying to model what's described to us as a reasonably practical situation. And the modelling involves us structuring our answer by setting things out in a step-by-step fashion. Remember, there is no other way of communicating with the examiner other than by what you are writing on your paper. For 11 marks, the examiner is going to need to see quite a few steps and in pretty much the right order. I am happy to accept, as I mentioned before, perhaps when you've learned how to do hypothesis testing, you've done things in an ever so slightly different order from the way I'm doing it. If that's the case, I would urge you to go back over this presentation and compare my way of presenting it with the way that you've understood, and try to identify what the differences are and why those differences might be there. What I would suggest is I don't think you can make any shortcuts above and beyond what I've already shown. I think if you leave any of my steps out, or something else sneaky like that, I don't think the examiner will be very impressed. We also had to use our calculator to actually calculate binomial probabilities, binomial cumulative distribution probabilities, and we also made use of statistical tables. Now, of course, you could say that you only need one of those things, but if you want to be a proficient mathematician, you shouldn't be put off learning new ways to do things that you already know to do. I mean, your calculator is presenting the answer in one particular way, but it's quite a neat idea to have a look through the tables and see how they work and to tie those two things together. And finally, the subtle thing in the hypothesis test is interpreting your outcome. Remember that we ended up with what's called a p-value, which is a probability, which was very small, and it was smaller than the significance level, that's the threshold level of the test. If your p-value is smaller than the significance level, then you reject the null hypothesis. You'll need to do a few other questions to see what happens in other cases. I won't go through that here for just so as not to confuse you, but make sure you try out some other hypothesis testing questions. You need to practice a range of questions so that you correctly interpret what happens depending on which side of the significance level you are. Also, you need to be familiar with two-sided or two-tailed tests as well. Let's finish with a very brief look at wider skills relating to this question. You should be aware that other questions will involve hypothesis testing relating to other distributions. This question was all about the binomial distribution. You'll also be asked to familiarize yourself with hypothesis testing based on the Poisson distribution and on the normal distribution. Next, a more general subtlety. This is the last thing I'll talk about here. One of the sneaky things about probability is you can't ask the most obvious questions, or the most obvious questions don't have meaningful answers, perhaps I should say. And this is why questions like hypothesis testing, when you first come across them, seem a little bit obscure. I'll give you a much simpler example. Supposing I toss a coin once. The obvious question that you might want to answer is, what is the outcome when I toss the coin? Now, of course, there isn't a good answer to that question. I can't tell you what the outcome is going to be. It's going to be either heads or tails, but I can't say for sure. And that's intrinsic to the nature of random experiments. And that's where all of this rather more elaborate phrasing of questions comes from. So in hypothesis testing, in the case that we had here, we got, 13 heads out of 15 tosses of a coin. The question we sort of wanted to ask was, does that show me that that's a fair coin? Is it a fair coin or is it not a fair coin? Well, I can't say. I can't say for certain. Benita can't tell us. Mark can't tell us if this is a fair coin. The best we can do is to calculate how likely or unlikely our observed outcome was, assuming that it was a fair coin, and then compare that with a predetermined threshold probability. Have a careful think about that. You'll see a lot of this kind of thing in probability. Things are a bit subtle because we are unable to ask the most obvious questions.